now that we understand the basic relationship in electrical power systems, such as power factor, true power, kVA, and KVAR, the basic elements of power itself, then now we can do a calculation by hand, and then also a calculation using the power triangle tool that we've created for you here. Okay, so let's take a look at this example by hand that I've got up on the screen here. Example 1 says you are currently provide 12 kVA to a brick manufacturing plant, and it's 24/7 it operates, and it has a maximum kW demand of 574 and a KVAR inductive load of 764 at peak. All of these are peak values that we have here. They want us to determine the power factor when we try to increase this to a 90% power factor as far as the plant is concerned. So we need to know what the existing power factor is, and then what we have to do to go ahead on and increase that to the desired power factor. So in the example, we have to determine 4 elements that we need to find out. The present peak power factor, present peak kVA, and the required KVAR capacitive values to be added to raise the power factor to 90%. And then there's another little question here. It says, will capacitors have an effect on the voltage profile of the plant? And then explain that. Okay, well, let's take a look at the first question here. We needed to determine the power factor. Well, we know that the power factor is just basically the ratio between true power over apparent power. So we knew it's the true power based on the kW that we have as far as the reading is concerned. At peak is 574 kW, and that the reactive power is actually 764 kVAR, and that's inductive. Okay, so just using the basic formula, power factor is true power over apparent power. Well, there it is here. 574 is the true power, and your apparent power is the hypotenuse of the triangle. Okay, and it's just the square root of the hypotenuse of the triangle, the right power triangle that you've already learned about earlier. So this gives us a power factor of 0.6, and that means that the existing power factor angle is 53 degrees, because we're talking about the arc cosine whose arc cosine value is 0.6, turns out to be 53 degrees. So this would be the present state. Then for the question number 2, the present peak kVA demand, well, that's pretty straightforward. kVA, we know what the kW, we know what the kVAR is. We still a right triangle formula for that, and there you have 956 kVA. So this is all the way you would calculate it by hand. So now kVA is uncorrected kVA demand, and kVA is corrected kVA demand. So we're going to come up with 2 values here. We're going to have an uncorrected kVA demand. That means we don't have capacitors involved. And then we're going to have a kVA corrected demand where we have capacitors. So that value of kVA of 956 is going to be reduced when we put capacitors on the system. So if we to raise the power factor to 90%, that means that the cosine of the power factor angle is 0.9. Therefore, the power factor angle is 25.8 degrees. So if we take our cosine of 0.9 and throw it into our calculator, then we'll get 25.8 degrees. Yeah, okay, so that's what we'll have, and only the KVARL value will change. The kW value remains the same. But remember that on a right triangle, we're talking about adjusting the reactive power. The kW is what it is. Okay, so it never changes. Alright, then the KVARC value needed to raise the power factor to 90% can be found as the difference between the original KVAR reactive inductive value, which was 764, and the corrective value of 278. Okay, and what I want to say here, okay, we can move on. Alright, therefore the corrected KVARL is equal to kVA capacitive times the sine of 25.8 degrees. So all this information can be done and computed using just Pythagoras theorem for a right triangle. Okay, and now you'll see how we'll do the same calculations when we wanted to find out what the final adjusted KVARC, which is the reactive power capacitor, needs to be done. So this is the hand calculations. It's numbers, but it doesn't really give you a real good feel as what it looks like when you're really working this out. So what we're going to do is that we're going to do the actual program to do this. Okay, I think I put the password in correctly. Let's see. No, I guess not. Let's try it again. Okay, so what happens, it brings up the electrical program for the different options available, and right now we're just talking about power factor corrections, so we'll click on that right now. Okay, here is the actual program up on the screen right now as to what we're going to use to do the same calculations that we just did by hand. And I'm going to just demonstrate it real quick and kind of give you some key points. The top section here is the data that you have concerning the brick plant itself. We know the voltage of the brick plant is going to be a 480 volt system. We also know that the kW demand, remember we had the kW demand of the system was 574, and we'll fill out the KVARL, the inductive demand, and then the desired power factor. So those are the key elements that we would actually put into the program to come up with answers that we need. Well, we've got three diagrams here: present state diagram, a computed result diagram, and then just a electrical schematic type diagram. Okay, the present state is going to reflect those conditions that how they exist in the field at the present time based on the parameters that were given to us. The computed one is going to show what the changes are as far as between the present state and the future state or computed state as far as the power factor and of the system is concerned. And then there's a schematic that just gives you a basic representation electrically as to what's happening after the meter if the customer is installing capacitors on its system. Notice that this capacitor is connected right directly below the main disconnect, so this is a capacitor bank would actually take care of the entire plant. Now that's just an option that the customer can do. They can put it there after the main, or they can put it on the individual motor control centers and regulate the power factor that way. So it's their choice. The other choice would be if the utility feels that the customer is not doing any proper control of their power factor, then the utility would have the same option of putting in the correct amount of kVARs on their system to control the power factor. So this gives you a pure number. It may be less than what it would actually be in reality because everything is not always on at one time. Remember, these are peak. Okay, so what we're going to find out is what the peak VAR requirement would be in order to adjust the power factor. Okay, all right. So now all we really have to do now is put in those values that were given to us. So 480 volts is the system, so 0.48. And the maximum kW that we were given was 574. And the KVARL, inductive reading that we were given was 764. And the power factor that we want to work our way to is 90%. So let's see what happens. So all we have to do is input into these four values up here and just come down and hit calculate. And now what is done is brought back what the present state is. We had 764 kVAR inductive, no capacitive load, 574 kW of true power, and then that gives us the actual kVAR parent power on the system of 955 kVA. So you can see that the power factor is 60%. under the current scenario, their KVA demand, their inductive demand, and what the amperage load is on their system, just going through the system without any capacitors on it. This is what it is once we adjust it to 90%. So if we bring the power factor from 60% to 90%, this is what it will have to have. You would have to have 486 kVAR capacitive kVARs to be added to the system, and the 574 remains the same. But what that does at 486 capacitive kVAR has dropped the actual inductive load down to 278. At the same time, instead of drawing 955 kVA as far as what the transformer that we are serving it would see, this would actually change and be reduced down to 637 kVA based on the capacitors that we put in, which are 180 degrees opposite of what the inductive load itself. Okay, so now in essence, here is what we would have. So schematically 574 kW is what we have, but now if we add capacitors, our inductive load is now just 278, and this is the capacitive value that we have. Notice one other thing here too, is that under the present state, there's 1150 amps flowing through the system. Okay, with capacitors, that drops it down to 768 amps. It's a big drop, very big drop, and consequently what that does is make it more cost effective. You would not have to use the full capacity or the current rating of the conductors if you're using the capacitors like shown here. So your current flow is going to change, therefore your voltage drop is going to change. So anyway, that's basically how the little program works itself. It just takes you through the present state to your proposed state. You can change this to 0.95 or 95% power factor and get new calculations, and then it'll show you here with the new capacitors, how much you have to put in as far as capacitors are concerned to bring it down even more to get the 95% power factor. So you can play with your power factors to determine what your capacitor ratings are in order to get things done the way you want it. Okay, well, I kind of went through that a little fast, but that's pretty much how the program works. It's pretty simple, but it gives you a nice visual as to what's going on versus looking at a bunch of calculations in a spreadsheet or on a piece of paper. Okay? Alright, that should do it. I'm going to go ahead on and stop the program.